Hi, I'm Jonathan Oxer, and this is SuperHouse. In the last couple of videos, we built two versions of a really simple DIY air quality sensor. It uses a laser scattering particulate matter sensor to detect stuff floating around in the air. You can build it without understanding how the software works, but if you want to really know what's going on, what we're going to do now is look into the source code that I've written that runs on the sensor. Now, I'm a really big fan of the Baud Group Embedded C programming standards, and over the last 12 months or so, I've been trying to use them more in my software development. So what we're going to see as we go through the source code are some of the conventions that come out of that as well. And I'll explain a couple of those along the way and why it's beneficial and it could help you in your own projects. Now, as you can see, the software is divided up into these four files. There's air quality sensor D1 Mini.ino, pms.cpp, pms.h, and config.h. The reason that I pulled that out into a separate file is that I wanted to put all of the configuration into one very neatly defined place. That way what you can do is go into the program, change the values there, and you don't need to be sifting through the source code of the main program to see what you need to change. Now, I know that typically what you would do is put variables like configuration values at the top of a project, but I really like the idea of pulling it out into a config file. It allows you to do things like save that config file separately from the rest of the project. It makes it easier to track when changes are happening, and it also just keeps everything encapsulated so that people aren't messing around with changing things in the main part of the code. I've broken the configuration up into a few sections and just put headings in here. So just SSID and password is obvious, MQTT broker is obvious, and then there are a couple of variables here which determine the way the reporting is done. What I've tried to do here is support two different reporting methods using MQTT. The simple method is to report each of the values separately. So the atmospheric environment PM2.5 variable, for example, could be reported to one MQTT topic. And then what you can do is, in the simplest case, you just subscribe to the MQTT topic that you want. But there will be many of them, one for each of the different values that we are reporting. The alternative is to have all of the values munged together into one JSON message, and then just report that as a single item. That's the way Tasmota does it. And what I've done, and you'll see in the code a bit later, is replicate the format that is used by Tasmota so that the same configuration can be used on the reporting side. And by default, I've got both of those methods turned on. You can just set them to false if you don't want them to report using that method. And then there is a topic for MQTT, which is just used for reporting when the device starts up. Now, this is something that I do on pretty much all of my projects that use MQTT, because it can be really handy to have a centralized topic that everything reports to, just so that you can watch it and see startup events. If you have a particular device that is rebooting continuously for some reason, maybe it's failing in some way and the watchdog is tripping and it's then rebooting, that'll become really obvious if you are watching a central topic which reports all startup events. So what I do is, in all of my devices, the very first time they start, well, when they start up, they subscribe to MQTT and they publish a hello world message into a generic topic, and they just announce themselves with their ID. And in my case, I just use the events topic. So every device that I have in my home automation system, when it starts up, it publishes to events and says, this is my ID and I'm alive. It makes it real easy to track down weird things going on, and it means that there is a predictable place that you can get those startup messages. And then we have a couple of variables related to the particulate matter sensor. There's the warm-up period. We know we need 30 seconds of the sensor running before we can take valid readings from it, and the reporting period. We want to report every 2 minutes, so I've just got it set to 120 seconds. You could set this to 5 minutes or whatever it is that is useful for you. And then I've got a serial baud rate and the hardware configuration, just defining which pins. So if you want to change configuration of the way the hardware is set up, you can do it in here, and you don't have to change anything in the main source code. Now, also within this project is pms.cpp and pms.h. It's a little bit unusual to see this sort of thing in an Arduino project, but what this does is bring a library in and embed it directly within the project instead of relying on it being externally existing. The reason for that is that the upstream library written by Marius Kaki has support for the standard particle and the atmospheric environment readings coming from the PMS, but it doesn't support the Ppd value, which is particles per deciliter. The library was forked by SwapBap, and Lena added support for Ppd values, but it's not so easy to install. Unless you download the library yourself and put it in place, you can end up with some issues. For example, if you have the official upstream library already installed, then you need to be able to specify which one is being used. To get around that and make it as simple as possible, what I did was took a copy of Lena's version of the library and I've put it directly into the same directory and then referenced it in the includes, which you'll see in just a moment. Before we get into the main code, have a look at pms.cpp and pms.h. Down here, what Lena has done is added values for decoding the payload where it gives total particles. This is the ppd count that we were talking about earlier. So now we get to the air quality sensor main program, and I've just put some comments at the top to explain the external dependencies. It needs some libraries installed through the library manager, and then there is the built-in library which we've included from SwapBap. Now the very first thing we do, and this is to make it obvious what's going on, is include the config file. That way if someone comes along and looks at this source code in order to figure out how to change it to suit themselves, the very first thing they'll come across is this reference saying you should make the changes in config.h, and they won't go digging further down into the code. So I always include that right near the top. And then we've got the libraries that are included. Most of these are assuming that they've been installed using the library manager, but you can see that pms.h, which is enclosed in double quotes here instead of the less than greater than symbol, and by including it like this, it will tell the compiler that it needs to look in the same directory for that header file and include it from there. That way, even if you do have the upstream version of the PMS library installed, it won't be used. It'll look for the local file instead and include that. Now the bulk of this program is based around a couple of state machines. One of the state machines defines what state the particulate matter sensor is currently in. So we define 3 states here. It starts off with an asleep state, which is when the sensor is shut down, the laser and fan is turned off. Then we've got a waking up state, which is once we've turned on the fan and the laser, it's clearing its test chamber, but it's not yet ready to take a reading. And then there is a ready state, once that 30 seconds has expired and we want to take a reading. The state of the sensor is stored here in GPMS state, and initially we set it to state waking up, just because we want to begin warming up the sensor as soon as the program begins. And then we've got a timestamp here, which is when the current state began. This tells us how long we've been in this state, so we know when to move on to the next one. We have a couple of flags here as well. You can see readings taken and PPD readings taken. Now PPD readings taken we shouldn't actually need. That's a bit of a hack to work around a problem that I found in the code. We'll get to that a bit later on. But what they do is allow us to keep track of whether we have received readings successfully from the sensor or not. Then just down below that you can see that there are variables to store all the values that come back from the sensor. SP are the standard particle calibration values. That's used during the factory calibration process. We don't actually care about that, but because the values are coming back, I'm storing them anyway. Then there is the atmospheric environment values. These are the values that you would normally consider to be things like the PM 2.5 value. Finally, we have the PPD values, or parts per deciliter. These are the values that we wouldn't get if we used the regular upstream PMS driver library. This is what's been added by SwapBap into her version of it, so that's why it's embedded in here. In these variable declarations, you can see that they start with G underscore. And at first glance, you might say, hey, that's Hungarian notation. And I can't stand Hungarian notation. I understand that it's useful in untyped languages like BCPL, but the problem that it's trying to solve largely doesn't exist in strongly typed languages like C, where the compiler is going to figure out problems if you try stuffing something into the wrong size variable or the wrong type. But the one place that this notation can be useful is showing scope of variables. This is something that comes out of the Baud Group Embedded C coding guide, and you can see it's got G underscore to signify that this is a global variable. That can be really handy when you're down deep in a program and you are assigning a value to a variable. You're not sure if it was declared within the scope of the current function or if it was something global. Problems caused by wrong variable scope can be really tricky. It's the sort of thing that can have you scratching your head for a very long time. So using this very limited form of Hungarian notation, where we just show global variable scope, can be really useful. I actually resisted the idea of using this G underscore notation when I first started following the bar group guidelines, but now that I've been doing it for a while, I've got used to it, it doesn't look jarring anymore, and it's actually really useful. You'll also see that I've declared these variables using things like uint32 underscore t, uint16 underscore t, and I haven't used int or long, the sort of typical aliases that you find in Arduino programs. That's because those aren't really very specific. They depend on the architecture. If you declare a variable as an int, is it 8 bits long, 16 bits long, 32 bits long? Like, who knows? Sometimes it's one, sometimes it's another. It depends on the target platform. So you can write code that will compile differently onto different targets in unpredictable ways. So if you want a 32-bit unsigned integer, then declare it as a 32-bit unsigned integer. Don't just use long and hope that that keyword is correct in the particular environment that you're compiling on. That's another thing that comes from the bar group's embedded C coding guide, and I think it really makes code a lot easier to understand. I've started doing this everywhere now. So if you see code of mine that's got things like int and long in it, it's all code. I don't do that anymore. Next up we have a couple of message buffers. There's the G Mqtt message buffer here, and you can see that I've set it to 150 bytes long. Now this is actually a bit of a problem, and this is something I still need to fix in the code, because the pub sub client by default won't let you send a message bigger than 128 bytes. And what I need to do is change it so that it sends an extended message. But for now I've just set it to 150 bytes, and we'll see the ramifications of that further down in the code. And we've also got a variable here to store the topic that's going to be used for receiving commands. Just down below that we've got variables to store the topics for all of the variables that we want to report. For example, we have a 1.0 micron atmospheric environment variable, and we've got a 1.0 ppd variable. Then the topics that can be used for reporting these are stored in these variables for later reference. And down here we've got the variable that will store the MQTT topic for the JSON reports. Next we have the settings for another state machine, which is the display. Because this device has a physical display on it, and we want to be able to toggle through different states using that button on the top, what we're doing is keeping track of what the current state of the display is, and then each time the button is pressed, stepping through to the next state. Then when we get to the final state, you press the button, it jumps back to the start again. So it just loops through a series of states and displays different screens. And down here we have the variable where it stores the current display state, and initially it sets it to the grams state. Then we have a couple of values related to the mode button. We've got some debounce in here, and we've got the current value and the previous value so that we can detect transitions. There are some settings for Wi-Fi, we don't need to worry about that too much. And the device ID. What I'd like to do with all of my IoT projects is have them derive some kind of a unique device ID and then use that in its reporting. That way what we can do is have a different MQTT topic for each device, or a group of topics, and it's predictable. What we can do is look at the ID of the device and then use that to construct the MQTT topic. What we're going to do just a little bit further down in the program is set this to a value that is unique to this device, but will always be consistent every time it boots up. Then we just have a couple of function signatures that don't matter, and then we've got the global objects. We're using software serial in this case so that we can communicate with the PMS and still have the USB serial interface working. Then we invoke the driver for the particulate matter sensor, and we set up an object for the data that's going to come back from it. We set up the SSD1306 display, and we set up the MQTT client. That gives the program all the resources it needs to set up its data acquisition and its reporting. Next we need to get it to apply the configuration and get underway. So down in setup we begin serial connection, and it just says hello, tells us what version it currently is. And we also set up the serial link to the PMS. This is where things start getting a little bit different to the way Tasmota behaves. What we do, because we've got the link now to be able to send messages to the PMS, is tell it to go into passive mode. We're going to wait 100 milliseconds and then tell it to wake up. With passive mode, what the PMS does is go into sleep until it's required, and then you can wake it up, take readings, and then send it back to sleep again. While it's asleep, the laser is powered down and the fan is turned off. It saves a little bit of power, maybe 15 or 20 milliamps. But importantly, what it does is it extends the life of the laser and the sensor so that instead of lasting 7 or 8 months, we can make this last for years. Now in the setup, we're telling it to wake up immediately because we want to take a reading as soon as the sensor is ready. And then just down below here, we can see where it defines the device ID. We're doing it from the esp.get chip ID function, which uses the ID of the particular processor that's on this board. It's essentially like a MAC address. So what we're doing then is just printing that to the serial console in hex format so that we can see what it is. Then we use the Adafruit OLED library and we clear the display, set up some things to do with the fonts. We just display on the screen what it is, the fact that we're starting up, and our ID. And we also display the device ID on the OLED. That way when it powers up, you can just read it straight off the screen and you know how to set up your MQTT topics. And just down below that, we can see how that device ID is used. The variables that we set up earlier, such as the 1.0 micron atmospheric environment MQTT topic, can now be populated. In this case, it's going to be tele for telemetry, slash, and then the device ID as a lowercase hex number, and then AE1P0 for atmospheric environment 1.0. You can see here that what it's doing is taking the chip ID and inserting it into here to form the MQTT topic. So by the end of this, these variables will all have unique MQTT topics defined in them. You can also see that we're only defining these if that particular reporting method is turned on. So if we're reporting MQTT topics separately, we define them here. And if we are reporting all of the values as a unified JSON object, then we define it here. Coming a little bit further down, and we just report those to the serial console. That way what you can do is plug the device into your computer and just open the serial console. And when it starts up, it's going to report all of the MQTT topics with its unique ID inserted into it. And then you can see exactly what it's doing. You can set up whatever you're using at the other end to read from those MQTT topics. Below that, we begin the Wi-Fi connection, and all it does is display on both the OLED and also on the serial connection where the Wi-Fi has worked. Pauses for 100 milliseconds, sets the input pull-up on the button pin because the button pin goes down to ground. That means that when the button is not being pressed, the value will be high. When you're pressing it, it will be low. And it sets up the connection to the MQTT broker. Below that is loop, and this may actually be a lot simpler than you expect. In fact, this is the entire loop. You can see it on the screen here. Most of it is actually just checking whether the MQTT is connected with Wi-Fi and executing anything that's needed to process MQTT messages. Below that, it does a check mode button, update PMS readings, and render screen. Obviously, there is a whole lot that goes on inside these functions, but what this means is that you can read through a loop and you can see the sequence of what's going to happen. Now, this is how I really like to set up my Arduino programs, because it allows you to see the overall flow of the program without having to wade through screens and screens of code. Often what you'll find is that the loop in a project is really, really big, and you'll be scrolling for ages and there are big chunks of functionality in it. What I want to be able to do is just look through the loop and almost read it like English. It says it's going to do this, and then this, and then this. And then the details of how those things are executed can be abstracted away down into functions. So my process when I'm writing something like this is often to do the functionality directly within the loop, and then to encapsulate it, stick it into a function, and put it out somewhere else in the code, once I understand more what the logical blocks need to be. And overall, this makes the program much more maintainable and easier to understand. And what we're doing here in the loop is just running as quickly as we can through each of these major tasks. If we were using a real-time operating system here, what we would probably do is set each of these up as a task with its own schedule. But in this case, we're just looping through as fast as we can go, and then allowing the major functional blocks to decide if it's time yet for them to do what they need to do. The first major function is the check mode button. And this is just a very simple thing. All it does is read the button pin, and it checks whether high is the previous state and low is the new state, which means that the button has gone from unpressed to pressed. It's just testing for a transition. Then it's got a little check in here to see whether enough time has passed since that transition, and if it has, what it does is increment the display state. So each time you press that button, it just increments the state by 1. And if it's hit the end, it loops it back to the first state. Then down at the end here, it just sets the previous button state to be the current button state. So we can safely call the check mode button function as quickly as we want to. In fact, it needs to be done very rapidly so we don't miss button presses. This could also have been done using an interrupt, but I've just done a little comparison here where it polls the button. The next major functional block is checking for new readings from the particulate matter sensor. Because we don't want to do this every time we run through the loop, there is a state machine to see whether the sensor is ready to give us readings, and there is a timer so that we can tell how long it's been since we last got a reading. So this is the implementation of the PMS state machine. Now there's something in this chunk of code that probably has you scratching your head. You're thinking, what the hell is going on there? It's this comparison right here. Now the traditional way of writing this would be the other way around. Most of the time, let's just do a version of it like this. You would see something like this. You take a variable and you compare it to some fixed value or something else, like a constant. So you say, if the PMS state is asleep, then do this. I've done it backwards here, and that looks really jarring if you're not used to it. But it's a little trick that allows the compiler to catch a certain type of subtle error that can really screw up your day in a very bad way. If you do it this way, the traditional way, and you forget to put one of these equal signs in, that is going to evaluate to true every single time, because it's going to take the value of whatever PMS state asleep is defined as, stuff it into PMS state, and then continue right on and execute the rest of this code. So instead of having a comparison, you've now got an assignment. The compiler will never even notice. It thinks that's perfectly valid. And so you will put your code into production or you'll run it, and then you may not even notice that this is going on. It might be, in this case, it'll be checking the sensor every time through the loop instead of doing it at the required interval. But if you have it structured this way, the way I've got it in my code, and you make that same mistake, the compiler is never going to let it work. It's going to say, hang on, that's wrong. You can't take the value of GPMS state and then assign it to PMS state asleep. It's impossible. So it just will not even compile, and you'll immediately see that error. Now you might think, oh, this is such a weird little programming error. You'd never come across that. Why would you structure your program in a backwards way to prevent something that's going to be such a rare occurrence? But this is actually a surprisingly common programming error. If you do it in a little program like this, you'll probably find it pretty quickly, because your program is going to be executing something much more rapidly than it should in this case. But I've seen this same problem crop up in code bases with millions of lines of code, where something might be executed only occasionally, and tracking down this particular problem is really, really hard. I saw one instance where this error was actually in a password validation routine, and the result was that the passwords just always worked. I've also seen it in a database function, and the result of that was, instead of finding a row in a database, it changed every single row in the database to have the same value. It totally screwed the production data. That's a really bad day. So now I've got in the habit of writing my comparisons like this. And then instead of saying, if PMS state is state asleep, I think of it as, is asleep the current PMS state? So you can still read it like English and it makes sense, but it will help you catch errors that otherwise might slip through and really come back to bite you. So next, if we're in the asleep state, what we're doing is a check to see whether we are close enough to the reporting time that we need to warm up the sensor. This looks a little bit strange as well. Ignore the times 1000, that's just to convert milliseconds to seconds. And what we're doing is taking the report period, which in our case is 120 seconds or 2 minutes, and we are subtracting the warm-up period of 30 seconds, so this will evaluate as 90 seconds. That's because we want to report every 120 seconds, but we need 30 seconds to warm up the sensor. So we're waiting until 30 seconds before the end of the reporting period, warming up the sensor, and then we can move on and wait until the end of the reporting period, and we know that it's ready to go. So if we are within that 30 seconds of the end of the reporting period, we send a command to wake up the sensor. And we also set a timestamp for when we entered this state, so we know how long the sensor has been warming up, and we put the state into waking up. Then the next part of the state machine just says, if we are waking up and we have now gone past the warm-up period, we are now ready to take a reading. And the third possible value of the state machine is if we are ready to take a reading, then we read the data from the particulate matter sensor. You can see here that I've used read until. That's a blocking version of the read function. There is also a pms.read, which is non-blocking. I've used the blocking function here because once we've got to this point, we want to make sure we get data. And because we only call this every 2 minutes, it doesn't matter if it blocks for half a second or so. The only thing that will happen is that the display will stop updating and it will stop responding to button presses in that period. It's a very brief glitch, so it doesn't really matter. And then we pass it this global variable called data, which is going to stuff all the values into. And then we can read them out. So PM-SPUG10 is just the standard particle, micrograms 1.0 value. We pull that out and put it into our own variable. Now we also set a flag down here saying AE, for atmospheric environment readings taken, is true. And you can see this is an assignment, so that's why I've got the constant on the right. That flag is going to be used later, and you'll see why we need that when it comes time to display this on the screen. Now just down here, we've got something weird going on. What I found is I'm not getting Ppd values every time I get data from the sensor. So all it's doing is summing the values that have come back for Ppd and checking that it's not equal to 0. That means we've got a value. So if we've got a value for any of these, it assigns them, and then it sets another flag saying that Ppd readings have been taken. And now that we've finished reading from the particulate matter sensor, we send it back to sleep. That turns off the fan, it turns off the laser. So at this point, we have values. We can report to MQTT and we can report to serial. And of course we update the flags for the state machine. These reporting functions are further down. We'll get to those in a moment. The other thing we need to do is render the screen. This is also called from in the loop. So it starts off by clearing the display, setting some things, and then this is the state machine for the display state. So if the display state is grams, then we display these values, but only if we've taken readings. That's because when our device starts up, we don't have readings yet. There's nothing there. So trying to display something doesn't make any sense. So if that flag has been set and readings have been taken, we display the values. But if it hasn't, what we do is just display a holding screen. This is where it shows particles microgram per cubic meter as the heading and preparing sensor and waiting for data. Now if the screen is in the Ppd state and we have readings taken, so that flag has been set, then we display values, and otherwise we just display the holding screen once again. Finally, our third screen is the info screen. And in this case, what we do is we just print the IP of the device, its MQTT client ID, various other things. We print Wi-Fi status. So this is earlier where we saw it say Wi-Fi OK. If it hadn't been able to connect, it would have said Wi-Fi failed. And then after that, it tells us the uptime in seconds just by taking millis and dividing it by 1000. Now I've got to ask you something, which is, what are you doing still watching this video? This feels like it's been going on for hours. It takes so long going through source code. Grab a drink or something, come back, and then we'll get back into it. Now we've already seen the 3 possible states of that state machine, but there's a default here, there's a fallback which shouldn't ever be executed. It prints to the OLED and it says unknown state and says what the actual state has been set to. Now that should never actually be reached. This is also part of the bar group recommendations, and it's a way of catching, once again, subtle programming errors. Anytime you have a case statement, you need to have a default as a fall through. Otherwise, if your code ends up with a value that you didn't predict, you can end up falling through the case statement and nothing will be executed, which can do really weird things. In this case, if for example we had forgotten to loop around the value when we were incrementing the button, and we ended up in a 4th state that we hadn't defined anywhere, we will get to this and it will display on the screen unknown state with the number, and it will become immediately obvious what's going on. And then at the end of all of this, we just update the display. Now we get to what is actually the bulk of the code, which is the MQTT reporting, but a lot of it is very repetitive, so it looks like a lot of code, but once you've seen one little bit, you've seen it all. Let's have a look at the first bit. The first thing is we check whether we've got readings taken using that variable that we set. We talked about that a few minutes ago. And then it just sets a message string. This is the value that's going to be pushed to MQTT, and it publishes it. So in this case we're publishing the particulate matter 1.0 atmospheric environment value to the topic that's been defined for that specific value. And all we do is the same thing for each of those. And we've also got the same condition for Ppd. So if we have valid Ppd readings, we report those values. And it just goes on and on and on. Then we get to reporting via JSON. And this is where we hit an interesting limitation. Back up here where we are publishing individual values, the actual message is very short. It's really just a number, whatever is coming back from the sensor for that value. But down here, what we want to do is create a chunk of JSON that's going to look a little bit like this. This is the example that came from Tasmota, so we can see what it looks like. And the actual message is quite long. Depending on what values you're reporting and how many values, this can easily go over 128 bytes. But the PubSub client library doesn't allow you to have messages of greater than 128 bytes. You can change that by editing the library and setting the MQTT max packet size, but that means that you are relying on editing something outside of the program and changing the environment. It's much better if you can do things like this within the program. Now there are a couple of solutions here. The obvious solution is to edit the library, but that's a pain. If you then try to compile this code in a different environment where the associated library hasn't been edited, you will get unpredictable things. What will actually happen is that if the message exceeds that size, it'll just silently fail, which is really bad. You don't know what's going on. So, two other solutions. One is that we can embed the library in the same way we did the PMS library. We could take the PubSub client library, change that value, embed it within our project, and then we could set that packet size to whatever we want. But then that's not really ideal either. It's taking a whole lot of extra code and bringing it in, and then if there are updates to that code, we don't get them within our system. There is a third option, and that is to use a special method within the library for sending large messages. I haven't changed my code to do this yet, but this is probably what I'm going to end up doing. That way we can use the unmodified library just from upstream, but we can still send messages greater than 128 bytes. And what I've done here in the comments is included a whole chunk of stuff, including the source code directly out of Tasmota, which I looked in to see how they were doing it, and the format of the message. So then what I can do down here is define what message I want and stick it into the message buffer. You can see here in the code that I've got a comment saying that this is the full message I want to send. So ideally, what I would be doing is sending all of these values. But if we do that, the size of the message exceeds the 128 bytes. So what we do instead is have another definition down here, which only reports some of the values. This brings us down to smaller than the 128 byte limit, and then it works. It's not ideal, but in the future what I will probably do is change this code to use the method for sending large messages, and then it can just send all of the values in one go. And once it's formatted that JSON and stuck it into the message buffer, it just publishes that to the unified JSON reporting topic. And that's really the bulk of the work done. Just down below that we report values to serial, and this is just doing the same thing over again. Once again, it's a whole series of very simple things. It's just echoing the value from that variable out to the serial console, and it just does it over and over again. And then finally, down near the bottom of the program, we have init Wi-Fi. This is called from higher up, and it just tries to make sure Wi-Fi is connected to the network. Likewise, we have this little helper which is Reconnect Mqtt. This is called further up, and if the MQTT connection is not in place, this is called and it attempts to reconnect. There's nothing particularly interesting in this little section, it's just attempting to connect. It's the same sort of thing that you'd see in any of the examples for MQTT. And then the very last function, this is the end of the file right here, so we're nearly done, this marathon, is the MQTT callback. Now this is the function that is called whenever a message comes into the device from MQTT. So if we are subscribed to a particular topic and then something is published to it, this method will be called. Now what we did right back at the start of the program was subscribe to the command topic, and the idea is you can then use that command topic to send commands to the device. It might be to do things like change the reporting interval or whatever. Right now we're not even using it. The callback has been defined and any message that comes into that topic will be passed through to it, but as you can see, everything is commented out. It doesn't do anything at all. So the infrastructure is in place to be able to handle incoming commands, but we're not processing it. Perhaps in the future what I will do is extend this so that we can send commands like change the telemetry period and then have that stored locally. And that's it. We're finally at the end going through all of this source code. Hopefully that wasn't too brain bending. And I really highly recommend that you go and check out the Baud Group's Embedded C Coding Guide. I found that it's really useful. It's a very sensible guide. It's got some really useful things in it that will help make your code more robust, a bit easier to read. I've seen lots of different programming guidelines over the years, and some of them are really complicated. The Baud Group's guide strikes the right sort of balance. It's got good, useful information and enough in it that it really will improve your programming, but it's not hundreds and hundreds of pages that are just too much to get into. So the link for that will be down below. Make sure you look below the video for the project page link. From there, I will link to the Baud Group guide. You can get it as a PDF, as a book, or just read it online. So, thank you for hanging in there. And next time, we're going to be back looking at how we can deal with the data that comes from this and report on it. So we're going to generate charts showing air quality over time and the values that come back from it. So in the meantime, go and build something awesome.